All right, so we're going to go through each question and explain what's going on here. I've got some stuff written down. Number one, when the equation above is balanced, the coefficients are reduced. What is the coefficient of water? So you can't start with water because there's oxygens all over the place on the right side. You probably started with lithium. You saw there were two lithiums and you went over and did a 2 in front of the lithiums. Then you tried to fix the hydrogens, which also impacted the water. And there were two hydrogens in the first compound and two hydrogens in the molecule. That was a total of 4 hydrogens, and you fixed the water. But then you checked to make sure that that still worked, because what if it was something higher than that? And so you checked the carbon. There were two carbons, and you fixed the two carbons, and then you cautiously added together the oxygens, and it worked. And so the coefficient in front of water had to be 2. All right, number 2, according to the balanced reactant equation above, how many moles of HI would be necessary to produce 2.5 moles of I? So the last part that they've got here, the starting with and this, that doesn't matter. How many moles of HI would be necessary to produce 2 moles of I2? So I've circled the two things that matter, HI and I2. I need twice as many HIs as I have as I2. So doubling up on the 2.5 gives me 5. Number 3, according to the reaction above, how many grams of aluminum, atomic mass 27, are necessary to produce half a mole of hydrogen at this and this? Well, the temperature and the pressure don't really matter. I mean, because we already have the moles. If they hadn't given us the moles, we might have to use like a PV equals nRT, but they gave us the moles. So we can just do the mole ratio. So I wrote down the moles of hydrogen, then I did the mole ratio from hydrogen to aluminum, which is 2/3, and then I converted it to grams, and it was 9 grams. And then I went to the next question. The exothermic process represented above is best classified. So we have a reaction. We have hydrogen peroxide becoming water and oxygen, and the bonds are changing, so we have new chemicals. So it's definitely either C or D because we have a chemical change. And in a chemical change, we have new compounds being made, and that's what D is all about. The covalent bonds are broken and new covalent bonds are formed. And you got to be cautious though, because a physical change, and only a physical change, isn't covalent bonds. A physical change is intermolecular forces. So if your liquid water becomes gaseous water, you're breaking hydrogen bonds between the water molecules. Physical changes are intermolecular forces being overcome or being formed, where chemical changes are covalent and ionic bonds being broken and formed. Number 5, let's see, we have, according to the literature, how many moles of potassium chlorate must be decomposed to generate 1 liter at standard temperature and pressure. So it's at STP, and it's a gas, so we're allowed to use that ratio. 1 mole of a gas is 22.4 liters. So that's what I pulled out. 1 liter, 1 mole is 22.4 liters. And then I did the mole ratio between oxygen and KClO3, potassium chlorate. And then I looked at my setups, and there was only one setup that matched that, and I was happy. All right, we have 2 reactants. We have azide, which is N2H4, and we have dinitrogen monoxide, N2O4, laughing gas. They're reacting together to make nitrogen and water. We're trying to maximize the mass of water. Well, we have 2 givens, so we're going to have to calculate 2 potential answers. And when we get those 2 answers, we're going to choose the smaller of the 2 answers because that's when the reaction would stop. So I worked both out, 8 over 1/32, 4, but my molar mass ratios and everything. And the mass of water that could be made based upon the N2H4 was only 9 grams. And that's when the reaction would stop because the hydrogen would be all used up. The other value would never actually be reached. All right, number 7. This is the hardest question. Of all 30 questions on this, this is definitely the hardest question. And we'll go through why. So we have a mixture of SO2 and O2, and they give us 0.2 moles of both. And they react and they make SO3. Well, how much SO3 are they making? So I did those mole ratios. I said, well, 0.2 of SO2 could make 0.2 of SO3. 0.2 of the oxygen could make 0.4 of the SO3. Now, both of these can't occur. You're either making 0.2 moles or 0.4 moles. So I thought about it for a minute and I realized, well, once I get to the 0.2 moles, I'm going to be out of sulfur. So that's when the reaction's going to stop. I can only make 0.2 moles of SO3. And once I've made those 0.2 moles of SO3, the SO2 is gone. It's been used up. But the oxygen hasn't been all used up from the O2. There's going to be a little bit of oxygen left over. And the reason this is important is because they want to know the pressure inside the flask. And all of the gases inside the flask would cause pressure. So we're going to have SO3 in the flask. We know how many moles of that. We're going to have some oxygen left over, but we don't actually know how many moles of oxygen. So that's what I'm keep working on the next page. If we used 0.2 moles of SO2, we could make 0.1, we would use 0.1 mole of oxygen during this reaction. So when the SO2 reacts with the O2, it uses up 0.1 moles of the oxygen during the reaction. So I did some subtraction to figure out how much oxygen would be left over. And as you can see there, 0.2 minus 0.1 is 0.1. So there's 0.1 moles of oxygen left. There's 0.2 moles of, oh, that's a typo in my answer key right there. It says we are make 0.2 moles of SO2. That's wrong. It should say we are making 0.2 moles of SO3. We're making SO3. I wrote the wrong thing there. And we have 0.1 moles of oxygen left over. So we have 0.2 moles of the SO3 and 0.1 moles of the O2 left over. So the moles of gas in the flask is 2 and 3. It's 0.3. It's 0.3. So that's the trickiest question because we have to figure out how much oxygen is left over and add it to the SO3 we made to figure out all of the pressure inside. Yeah, like for this one, like that's pretty difficult. I totally think that's a difficult question. And a lot of people would jump right to, they would jump to C. A lot of people would jump to C. They would, I've got the moles of SO2, and that's what C is. C is the moles of SO2, R, T, and V. It does not have the moles of SO3 and O2. So that was a tricky one. Hope you followed that. All right, back to an easier one. We're reacting, and we got to figure out the limiting reactant. The one that gave us moles, we just did the mole ratio to the NO. For the other, it gave us the volume and the molarity. That 6/1 there is the molarity, written as a ratio of moles to liters. And then we did the 1:4 ratio, and then we have these two answers, and we're going to go with the smaller answer. The smaller answer is when the reaction stops. So it looks like the HNO3 is limiting our reaction. Number 9, we have a 1 liter aqueous solution of sodium chloride and calcium chloride. What's the minimum moles of silver nitrate? Okay, so with this one, we're trying to take all the chlorine out of the water and bond it with silver. And we need to figure out how much chlorine's in the water to figure out how much silver to remove. So how many moles of silver from the salt? 0.1 moles of salt, so that's 0.1 moles of chlorine. And then how much chlorine from the calcium chloride? There's 0.1 moles of calcium chloride, but that has 2 chlorines, so it's actually 0.2 moles of chlorine. So with the 1 from the chlorine, the salt, and 1 from the calcium chloride, we add that together, and we have 0.3 moles of chlorine. So we're going to need 0.3 moles of silver to react with it. Because for every chlorine, there's a silver. So since there's 0.3, we'll need 0.3. precipitate reaction is a solid made from aqueous solutions, so the answer is B. I'm looking at my other answers, and A does make a solid, but it's not a precipitate because it's not coming from aqueous solutions, so not that one. Okay. 20 more questions. I combined 12 and 13 together. All these reactions are the same again. We have precipitate reaction. We're looking for a solid created from aqueous solutions. That was D. Yeah. And then in 12, I went through and worked out every oxidation number because I needed to know which one was oxidation reduction, but the same reactant underwent oxidation and reduction. So bromine in C is Br2, so that has no value for its oxidation state. And on the other side, it's Br minus 1, that's a minus 1, but it's also in the BrO3 minus 1. So I worked out the oxidation state for that bromine, and it's plus 5. So some of the bromines are going from 0 to minus 1, some of the bromines are going from 0 to plus 5. So some are gaining electrons and some are losing electrons. So the bromine is undergoing both oxidation and reduction. Now, I think it might be easier to just eliminate some of the others. For instance, D is a synthesis precipitate reaction, so I could eliminate that one. E, I worked out the oxidation states and I was fine with that. In B, sulfur is changing once, oxygen's changing once, so it couldn't be undergoing both. And then in A, we had the selenium changing, and we had the chlorine changing, but there wasn't one particular thing that appeared multiple times. So, yeah, C was the answer because the bromine was going from 0 to -1. At the same time, it's going from 0 to plus 5. It's time to make a solution. We want to make 2 liters of 0.1. So first I did the math on how many moles that would be. Then I grabbed the molar mass that they gave me and I figured out how many grams. It was 42.8. And I felt good about that because several of the answers said 42.8. And I need to add water until the final homogeneous solution has a volume of 2 liters. So when they say a final homogeneous solution, they're implying that they mixed it together. Kind of wish it said mixed together, but it doesn't. All right, this took up 3 pages in the packet because the sizes were all messed up. But first I started with actual question 14. If the ions were all separated properly in diagram 1 and 2, and I wrote the reaction there, as you can see, and I figured out that the sodium and the nitrate, when they come together, will still be aqueous, but the silver chloride would be a solid. So then I looked through the pictures and I found the proper representation. The first picture, A, had the silver and the chlorine up at the top together. Why would they be floating? They wouldn't be. And then the aqueous ions, sodium and nitrate, are together when they should be split apart. We run into those 2 things a couple times, and only answer D has it done right. I put that on the top right. D has the silver and the chloride as a solid at the bottom, and it's got the sodium and the nitrate split apart as ions. Yay! Number 15, again, is look for who's changing their charges, because it's an oxidation reduction reaction. And also synthesis. Synthesis means making one product. So making one product, I could cross D off, I could cross C off, and I'm down to A, B, or E. Then I went through and I was like, well, who's changing their charges? And worked out the charges of things. I didn't do B because it was precipitate, but I did A. That one is pretty obviously the answer because the magnesium's getting a +2 charge and losing electrons, while the oxygen's gaining its 2 electrons. E, it took me a while to noodle out what was going down there with the silver. It's like the silver is in brackets with the NH3, that's 2 of those, but it's only got a +1 charge, and it took me a while to get those oxidation states down. But if you look, The nitrogen's a -3, the hydrogen's a +1. That would balance itself out already. The nitrogen and the 3 hydrogens add up to 0. There's 2 of those, so it's 0 and 0. And the silver's a +1. Oh, the silver's still a +1. That's not a redox reaction. Yeah, it's a little weird. In number 16, we just had to figure out what to do with the electrons. We had to get the electrons equal by doubling and tripling the 2 reactions. And when we double the first reaction, that means the coefficient for aluminum is going to be 2 and 2 and a 6, and for zinc it's going to be 3, 6, 3 to balance it all out. 17, this is a limiting excess problem. You take both of your givens, take the mole ratios, figure out which one would produce less, and the second reaction produces 20 moles of hydrochloric acid, so that's what we go with. 18, you have 2 mole sample of this, reaction excess. That means way too much NaOH. The reaction is repeated, but this time you got half as much fluorine, but the same amount of NaOH. Well, they cut the amount of fluorine in half, so they're going to get half as much product. Half as much reactant, half as much product. Number 19, we're mixing 20 grams of crystals. How do we know we didn't form a new compound? So a couple of these are odd answers. Solution does not change color after stirring. Sometimes the solution changes color, and then when you turn it back into a solid, the color disappears. D is the only one that kind of works. After the water's evaporated, the white crystals in the beaker have a mass of 20 grams. They start off as white crystals of 20 grams. They finish as white crystals of 20 grams. If there was a new compound, it's highly, highly unlikely that you would start and finish with 20 grams. You're probably going to, if you had a new compound be formed, it would start with 20 and finish with a different mass because there would be different elements attached to each other. Number 20. I wasn't sure, based upon that initial data, which one of those was limiting the reaction. So then I did the math, as you can see. I did liters times molarity, then my mole ratios, and it turns out that 100 milliliters of one thing, 100 milliliters of the other thing, both produce the same mass of MgOH, the same moles of MgOH. So they're both limiting. Well, if you want to double the amount produced, you're going to have to double both of them. Yeah, so doubling both reactants will double the amount produced. Because neither one of them is an excess, you do need to double them both. Which of the following is true regarding the reaction above? There's lots of mentions of oxidation states of the answers. So I looked to try to figure out which oxidation states were right and wrong. I went through and wrote the oxidation states on the top. Hydrogen's weak, selenium's a -2, then O2, F2. That's the one time oxygen's going to be positive. When it's with fluorine, fluorine gets a -1, so the oxygen has to balance it out. And then on the other side, oxygen's a 0, and kind of working that way. And after doing that, I realized that many of the other answers are wrong. Hydrogen's a +1 on both sides, fluorine's a -1 on both sides, unless fluorine's alone, and it's not alone up here, it's in a compound. And I don't know what a disproportionation reaction is. I don't know what that is. I just wrote, what? Feel free to look up disproportionation reaction and let me know. Just tell me in class right now. Number 22, we haven't done equilibrium problems and acid-base reactions yet, so this really shouldn't have been on this worksheet. Sorry. 23, this is also kind of in the wrong chapter for some reason. It's in here. This is a chromatography question. The hexane travels up the paper. Hexane is nonpolar. Looks like compound X travels with it really well. So compound X is probably nonpolar because it traveled so far. Compound Y didn't travel as far. It's less attracted to the hexane. Maybe it's more attracted to the paper. So since the paper is polar, it's going to slow down things that are also polar. So compound Y is more polar than X. For this one, which requires a lot of cautious reading, the number of MnO4 ions must be equal to which of the following? We're looking for MnO4. So you have to kind of, I feel like these are written a little bit in reverse. So if we want to know how much MnO4, but you had this much iron. So if you have 5 irons, you need 1 MnO4. That's 1/5 the amount of iron. If I have 8 hydrogens, I need 1/8 the amount of hydrogen for my MnO4, and that says 8 times. So the others are all just badly using the ratios. You have to cautiously use the ratios. And even when I wrote down the ratio, I kind of wrote it upside down. We need 1 mole of MnO4 for every 4 or 5 moles of iron. So we need 1/5 the amount that we have for iron. I just wrote that backwards. Number 25, we're looking for the right net ionic equation. And a net ionic equation, the spectator ions have been removed. So in C, we should be removing all of those spectator ions, which would be nitrate and potassium, because nitrate and potassium are aqueous with their same charge on both sides, so they don't react. And B doesn't even make a precipitate. And D is a good reaction. They just didn't remove the spectator ions. So that's why A is the right answer. They removed the spectator ions, and the answer shows the precipitate, the solid. For 26, it doesn't ask for all of these charges to be written down, but I just decided to. Carbon is stronger than hydrogen, so I wrote down the hydrogen charges first. I wrote down those +1, +1, +1, +1. And then I was like, well, if the hydrogens are +1 and +1, the carbon must be a -2 to balance it out. And then I did the same thing on the other side. I said, oh, there's 3 hydrogens that are each a +1, so that carbon must be a -3. So the carbons are gaining an electron as the hydrogens lose them. Ooh, that's an oxidation reduction reaction in which hydrogen is oxidized. The hydrogen's losing electrons. I just kind of started this one out by writing what the copper was doing, and then I read the answers. So yeah, the copper is going from Cu to Cu+2. It's losing electrons. It's being oxidized. And I looked at those answers, and I said it's got to be A or B. Which one is accurate? The copper is becoming +2, so it's got to be B. I just checked silver to make sure that was right. Silver's going from +1 to 0. Yeah, it's gaining an electron. This one's slightly tricky. You just got to count how many of each molecule are over there. I wrote the reaction. Carbon monoxide plus oxygen makes carbon dioxide, and I balanced it, which is really important. You got to balance your reactions, people. Then I wrote down how many pictures are present before the reaction. I have 4 of those COs, and I have 3 of the O2s. I miscounted for a second. That's why the little scribble's there. But we don't start off with any CO2s. As the reaction goes, the limiting reactant is going to be used up. So the limiting reactant's CO, if you kind of think about it, 2 COs make 2 CO2s. 3 oxygens would have made 6 CO2s. So we're using up the CO. All the CO's gone, making CO2, and we're leaving some of the oxygen behind. I looked at my answer choices, and B has the right ratio left behind. D has all carbon dioxide, which they somehow ended up with 6 carbons instead of 4 carbons. That one's why you can cross D off. And C is wrong because C has oxygen with 2 carbons and oxygen with 2 carbons. C is an example of a person who doesn't read the key very cautiously. 29, the volume of distilled water that should be added. Well, okay, so we're doing a dilution. We're turning 6 molar hydrochloric acid into 0.5 molar hydrochloric acid. So I do the math, 10 times 6 is equal to V2 times 0.5. I divide the 0.5 over, and the new volume is going to be 120 milliliters. This is 120 milliliters after the dilution is done. To dilute it from 10 to 120 milliliters, you need to add 110 milliliters. And unfortunately, they have a typo with their correct answer, 110, and then they have a capital M. What does capital M stand for? Mega. So they accidentally said megaliters, which is thousands of liters? No, that would be kilo. Millions of liters? Yeah, that's 110 million liters. Yeah, they totally messed that up. They meant a lowercase ml. So, yeah. And again, it's 110 because you're going from 10 to 120, so that's how much water you would add. And 39, the copper is being oxidized because it's losing electrons, and the nitrogen is gaining electrons. You can see below number 10, I worked out the oxidation states for the nitrogen and the copper so that I could feel good about my choice. This is the final question, and I hope you guys are doing well, and I'll talk to you later.